All right, this week we're going to finish up the content for Unit 2. So we're talking about packets, protocols, and internet dilemmas. So next week we'll be on to the Unit 2 assignments. So there's three assignments for you this week. One of them is going to be your Cornell notes, right? So we're looking at, lessons 5 through 7. So 5 is about packets, 6 is about different protocols, HTTP, DNS, HTML. We're going to get into some TCP, UDP, and then lesson 7 is about internet dilemmas. So these are like things going on with the internet in regards to computer science that you guys need to know about for this test. So there's going to be 4 videos for you. One of them is going to be this lecture. There are 3 shortcode.org videos that are on YouTube that I want you to watch. Again, they just do a really good job with the examples and the graphics, kind of explaining this stuff with kind of better visuals than what I have available to me. And then your second assignment is going to be the MCQ practice 2-2. So you need to make sure you're signed up on the College Board. This one is 20 questions. And then that third assignment is just your weekly check-in. So let's go ahead and get into it. All right, so we're starting off with lesson 5. This has to do with packets, right? So before we start talking about packets specifically, there's two protocols that we're going to introduce to you. One is the UDP protocol. The other one is the TCP protocol. So they're both ways that we can send information across the internet, right? This unit is Unit 2. The internet, we're talking about how we get information from point A to point B. So last week, we talked about what a protocol is, the IP protocol and how IP addresses fill into that. And then we got into the idea of routers being these devices on the internet that are responsible for sending information across the internet, the idea of routing. So we have multiple routers that are built into place so that data can send through multiple paths to get to where it needs to go, which got us into the idea of a path. So whichever route that the information takes, that is the path that it followed, and data can follow different paths as it goes. It's not always going to take the same path. Even a single file that we send, right, like a video, it's going to get broken up and sent over different paths to get to the same destination. That's just how the internet works, which got us into the idea of redundancy. So this idea of having multiple connections or paths in a network so that communication can continue. And then fault tolerance, which is a way that we achieve redundancy. Fault tolerance was how we would have multiple devices available to us in case one goes down, right? So we're kind of tolerant if something fails, that we have another route that we can take, which is redundancy, which creates the multiple paths, which is what routers and routing does for us. So when we are actually sending this data, this is where TCP and UDP comes in. So we're kind of jumping around on the Cornell notes, but when we're talking about UDP, UDP is a protocol, so it's a set of rules that have been established that everyone follows, that sends packets quickly with very minimal error checking, and it does not resend any lost data. So we use UDP when we want to focus on speed, right? We just need to get something from device A to device B, and we don't care if a little bit's lost. We're just looking to get it from A to B as quick as we can. The second transmission protocol is TCP, the Transmission Control Protocol. This one is slower, but it is more accurate. So for this one, if we're sending devices from computer A to computer B, we will make sure that every piece of information makes it from A to B. So whereas UDP is more concerned with speed and we're okay with losing a little bit of data, TCP, we're more concerned with accuracy, right? So TCP is a protocol that ensures accurate data transmission. It does check for errors, it does reorder packets, and it does resend anything that's missing. Right? So I've mentioned packets a few times. Our definition for packet is a small chunk of data sent over a network. So if we have a large file that we need to send, This file will be broken up into hundreds, thousands, or tens of thousands of packets, and each one of those packets gets sent off individually, which brings us back to the idea of routers and paths, right? Every packet that gets sent they're going to follow different paths. They're going to take a different route from A to B. And this is where the TCP and UDP really kind of comes into play. This idea that with TCP, because maybe I'm sending for a song, tens of thousands of packets that make that song up. If I need to make sure that it gets to the user and that everything is put back in the correct order, I will use TCP. Right? If I'm just streaming this file to a user, and if they lose a little bit along the way, I'm okay with that. It's just going to buffer a little bit. Music might pause on their end and then pick back up. Then I would go with UDP. Right? So again, UDP is for sending these packets, these small amounts of data that make up the entire file, where we're looking for speed, right? Not so much error checking, not so much making sure everything gets there in the right order. We just need to get it over there. TCP is when I want to send those packets, but I need them put in the right order, and I need it confirmed that they received everything, right? So one of the key parts of TCP is when I send, 10,000 packets from A to B, computer B will confirm back to computer A every time a packet's received, so I can check on computer A and make sure that I got a confirmation for every single one of those packets, right? So kind of how it does this gets into the idea of packet metadata. That's additional information or additional data that's attached to each and every packet that includes information such as the sending IP address, the receiving IP address, the packet order. All of this is there so that it knows where A is, where B is, and it can confirm if the transmission protocol requires, whether we're using UDP or TCP, back to A to confirm that every single packet was received. All right, so kind of looking at these definitions again, right? The packet is a chunk of data that's sent over a network. We have UDP, a protocol for sending packets quickly with minimal error checking. TCP, a protocol for sending packets that does error check and receives that packets, or ensures that packets are received and properly ordered. And this idea of packet metadata, right? Adding to packets to help provide additional information other than the actual data, right? When we're talking about packet metadata, if I'm sending a song, the song is the data. The metadata is that additional information, where it came from, where it's going to, what packet number this is, all of that stuff. All right, so when we talk about data stream, I know that one's not on here. That's information sent across the internet as a sequence of packets, right? Actually, this one is on here. Information passed through the internet in packets. So whenever we take a file and we're going to send it, we're saying that's a data stream. So kind of a visual, again, you don't have to memorize this. This just kind of shows you this idea of packets and metadata, right? This is called the OSI model. And there's 7 layers to it. Traditionally, there's a couple different versions. We don't worry so much about the details on these top 3. Just know these top 3, this creates the data, right? So if we're creating a song, this data, that would be simply the song. What you see in orange is as we go down in these different layers, which we're going to get to more in a little bit, we start adding this metadata to it, right? So there's some segment header that gets added. There's the packet header, right? The packet metadata. Then the frame, right? So all this orange, teal, purple, even this burgundy, that is all metadata that's being added to the actual data, the actual song that's going to be sent. Right? All of this gets stored as zeros and ones, and then we break those zeros and ones down into tiny little chunks that have this additional information. Each one of those tiny chunks is a packet that gets sent in that data stream. All right, so this is just kind of a visual showing you that metadata and how it works, right? We just attach it to the zeros and ones that make up our actual data. So really quick, before we kind of get into lesson 6, we have those questions for lesson 5. So I'm not going to specifically give the answers, but I am going to kind of key you in on what you should be talking about. So why is data broken into packets instead of being sent as one continuous message? What you need to think about here is efficiency. And this idea that we have redundancy, we have fault tolerance, we have multiple paths, we have multiple routers. Things get congested, things get clogged up, things go down. So this idea of breaking our large data files up into small chunks that can more quickly be sent using these tools that we have, routers, routes, path, fault tolerance, redundancy, it increases the efficiency. How packet metadata helps route and deliver and reassemble messages. You need to think about that packet metadata that we talked about. So this idea of packet metadata is going to tell those routers where it came from, where it's going to. You should be talking about, redundancy, fault tolerance in there, and kind of reordering those packets. When we're talking about the difference between TCP and UDP, you should kind of be keyed in on TCP prioritizes accuracy. So it's going to confirm that every packet was received. It's going to confirm that the packets are in the correct order. UDP is going to prioritize speed. So we're not going to do so much error checking. We're just going to send it off, right, for like streaming videos or listening to music or online gaming, right? We're just going to send it off and hope it gets there. If it doesn't, it's fine. We're just going to move on. And then, why might packets arrive out of order? Again, you should be talking about routers, routes, paths, and packets, right? We break it up into small packets so it can follow different routes and paths and go to different routers to account for things breaking or parts of the internet becoming too congested and going too slow, all of that stuff. All right, so looking at Unit 6, we have a couple more definitions. One of them is DNS. We talked about this a little bit last week. That's that domain name system. So that's the system responsible for translating domain names like example.com into the IP address, which uses that IP protocol. A domain name, that is just like that human readable name that individuals or companies purchase, right, to make their site more easily accessible to end users, right? As humans, we're good at remembering domain names. We're not good at remembering IP addresses. So DNS helps us bridge that gap. People always say like the internet and the World Wide Web, they talk about them like they're one thing. They're really different. So when we talk about the World Wide Web, it's a system of linked pages, programs, and files, right? It's a part of the internet. The internet is this connection of all these routers and paths and devices that create this global link so everything can communicate. When we're talking about the World Wide Web, we're specifically talking about a system of linked pages, programs, and files, right? And this gets us into HTTP. This is another protocol. HTTP stands for Hypertext Transfer Protocol. That is a protocol for computers to request and share the pages that make up the World Wide Web on the internet. So whenever we are requesting a web page, right, if you're going to go to google.com, it is using the HTTP protocol to send that page back and forth, right? There's no mention in the Cornell notes or slides about HTML, but you will see it on the AP exam. HTML is what we call the hypertext markup language. So technically, HTML is a language that we use to build our web pages so that it gives it the structure, the colors, along with CSS, which is cascading style sheets, that determine how our page looks, right? So when these HTTP requests are going back and forth, right, these requests for files or pages, the information that's actually being sent back and forth is HTML, which dictates to that browser how to display that page to you, the end user. So for the kind of looking at this visually, when we make a request using HTTP for an HTML file, there's two different ways to do it. One of them is called a POST request. The other one is called a GET request. All this really means is when I make the request for the page, I'm going to send additional information, right? Like let's say it's a login page. So on that page, the user types in their username and password. I will then make an HTTP request to a server to see if that username and password matches a user in my system, so I can return them back a page where they are now logged in. So when we're talking about that additional information, the username and password, I can send it either using a post or I can send it using a GET request, right? If you look at these example, URLs, when you make a post request, you just request the name. There's some additional like meta information attached to this request where you would find that username and that password. That's a post request, right? When it's just attached as like metadata to that request. In a GET, we actually use this little question mark and then we use this key value pair to add that information. So we're not attaching metadata, we're actually putting that information in this URL as an extension of this domain name. So essentially what I would say is, example.php question mark username equals, and I would put the username, and then I would put a little and sign and say password equals and put their password. Right? Now I know this isn't a super secure way, this isn't technically how it works, but it's a good example. But you do need to kind of understand this idea of post and GET for your Unit 2 project, right? So when we make the HTTP request for web pages, we can use either post or GET, and that just tells the computer how it can find the additional information that it's going to need to process that request on the server so that it can send back through an HTTP or HTTPS request that HTML file. So kind of looking at this from a global bird's eye perspective, we have our browser, we type our domain name, our URL, which is just a uniform resource locator, into the browser, we hit enter. That generates our HTTP request that can use either a GET or a post. So when we use GET, we do not need to send additional information along with our request. It's in the URL. When we do a post, we do need to send additional information, which would be that metadata, right? The server is going to receive either the GET or post request and process that, and then send that HTTP request back to the browser that asked for it, using HTML for that actual file. This certificate here, this is what determines whether we use HTTP or HTTPS. Right? S just stands for secure. Nowadays, pretty much every website has a certificate, and we always use HTTPS. Back in the day, that wasn't as common, I would say. So it's just kind of like a heads up, right? If you're on a website and you don't see that little lock symbol, you don't see HTTPS in that URL, that means that page is not secure. If they're asking you to put something personal in, or a credit card number, or a password, do not do it, right? Essentially, the S just means that when that request is made, it's going to be encrypted and it's safe and secure. Other people would have to do some work to try to get at that information, right? It's not just sent in plain text so anyone can read it. So kind of going back to this idea from lesson 5 of, data getting broken up into packets, and every packet having this metadata telling us where it came from, where it's going to, the packet number, whether it's TCP or UDP. What we need to create is kind of this, I just call this the APCSP OSI model, right? This is kind of our bird's eye view of everything that we just talked about, and your Unit 2 project is going to have you generating your own version of this to demonstrate to me that you understand it. So what we have here is this computing device, along with our OSI model, which, it kind of looks upside down because we're going to the physical layer up top. Just understand we're looking at it from this encapsulation side. So I just kind of flip this so we can kind of work our way up rather than work our way down. So the first thing that we have is our encryption, right? So when you see SSL or TLS, you need to know that that's an encryption protocol, and it tells that computer how to encrypt that data so that not everyone can read it. Once it gets that, right, again, we have the data, right? So now we add a little bit of metadata that tells us that encryption, SSL or TLS. It then goes to the next layer of that OSI model where we're going to add some more metadata to tell the computer whether we're using TCP or UDP. Do I care about error checking and accuracy, or do I care about speed? So I add that as some metadata. And then it goes up to the next layer where I'm going to add the IP protocol, right? So this is where I'm going to tell it where it's coming from, where it's going to, and essentially how many packets I have, so that it can reorder it if it needs to, depending on which transport protocol I used. And then it hits this physical layer, right? We call this the physical layer because this is the hardware on your computer. This is the cable that it's going to go through to get to your router. All those physical parts where now we're dealing with the zeros and ones and packets. So, if we're requesting a website, we work our way up. So now we have a bunch of packets with a bunch of zeros and ones that has all of this data for us. The first thing it does is it makes a call to the DNS. So it can translate that domain name that you gave it, example.com, to an IP address. Once it returns that IP address back to us, we then make our request. Right? This is where that HTTP. So this request gets sent off using either GET or POST to our computing network. Right? This is just the network of routers, paths, redundancy, fault tolerance. Each packet's going to follow its own path, right? It's will not happen where every packet goes the same way. Every packet's going to take its own path. But eventually it's going to make it to like our business's router, or we have a router at home with all these devices connected to it, and that's kind of the final stop where it's then sent to the actual device that needs the information, right? So these are the different computing devices. This is a computing network. This is a computing network. Kind of understanding how this request is made, right? This idea of a domain name, HTTP, post GET to the server, HTTP versus HTTPS, certificates being sent back, and then this one where we kind of put it all together. This little arrow right here is this slide. That's the bulk of your Unit 2 project, right? Being able to take all of this stuff that we've talked about and put it into a slide that demonstrates to me that you understand how all of this works. So looking at the questions for lesson 6, how does domain name system, the DNS, translate domain names? Just kind of remember that DNS, it's a directory that matches domain names to IP addresses. Right, so it helps us get from point A to point B. Why is DNS essential for allowing internet to scale? Again, we're constantly adding new devices. We're constantly creating new domain names. This DNS system is where those tables are created and stored. So when we connect new devices to the internet, it sends off its location to this router, which sends it to the router it's connected to, and it kind of makes its way across. Right, so that there's a good chance someone in here knows where this is, and this one's always going to know where these are. All right, so what problem does HTTP solve when dealing with, the World Wide Web? It's basically the standard. It's the protocol for computers or clients to request web pages and for servers to then send that information back to us. And how do DNS, HTTP, and lower level internet protocols like IP kind of work together? That's what this graphic is, right? DNS finds that server's IP address, HTTP requests the web content, and then IP, TCP, UDP kind of dictates the routing, the packet delivery, the reliability. And that kind of closes up lesson 6. So lesson 7 kind of changes directions and starts talking about internet dilemmas. So these are like issues in computer science that are, it's a problem for us now, and we need to kind of figure out how we're going to handle these. So we have this idea of the digital divide. The digital divide is just this idea that differing access to computing devices and the internet based on, socioeconomic, geographic, or demographic characteristics. So some people can afford the internet, some people can't. Some people live somewhere where they have easy access to the internet, right? Like we live in the United States. There's very little places you go where you do not have access to the internet. That is not the case in other countries. Even like economically, I used to teach in Hemet, and I would say approximately 2/3 of my students did not have a computer at home. And if they did, they probably could not afford internet. Whereas here in Temecula, I would say probably close to 85–90% of the students have multiple computers at home and have multiple ways to connect to the internet, whether it's their home network, phone, sitting at a Starbucks, right? This is the digital divide, this idea that not everybody has equal access to the internet. And it kind of gets into two more issues. One is net neutrality. So net neutrality is the principle that ISPs should treat all internet data equally without blocking, slowing, or providing certain content. So an ISP is an internet service provider. So we're talking about T-Mobile, Verizon, Comcast, all these companies that are in business to give internet access to individuals. There's been discussions over the years on this idea of net neutrality, right? For some traffic, they want to slow the internet down. For other traffic, they want to speed it up. That gets into, some tricky waters when it comes to, ethical concerns, equity, access, influence globally and locally. Like in China, they do not have equal access to the internet. There's parts of the internet they can't get to. Their ISPs shut it down. There's recent events in Iran. They have shut down the internet. They've even shut down satellites so people can't access the internet. This gets into, the digital divide and net neutrality. When we talk about internet censorship, we're also talking about this practice of blocking or limiting access to online information, websites, or services. Usually when we talk about internet censorship, we're talking about by governments or organizations. So again, the idea that like Iran and China are actively blocking parts of the internet for people, right? So they can't get certain information that they don't want them to have. That is internet censorship. So you need to know internet censorship, net neutrality, and the digital divide, both for the multiple choice tests next week and for the AP exam. So when we're looking at those questions, what is the digital divide and how does it affect individuals and groups differently? Again, the digital divide refers to unequal access to computing devices and the internet, which can limit opportunities for education, employment, communication, and civic participation for certain individuals or communities, but not everybody, right? It's this divide that's kind of slowly happening between people that have it and people that don't. Why do internet dilemmas raise ethical concerns about equity, access, and influence? Again, these dilemmas affect who can access information, who gets heard online, who benefits from digital technologies, and that raises questions about fairness and equal opportunity. So what is net neutrality and how could changes to net neutrality impact internet users? Net neutrality ensures equal treatment of all online data, so we're not picking and choosing which data is getting sent somewhere and not sent somewhere, or the speed at which it's being sent or shared. So without, net neutrality, ISPs could favor certain websites or services, potentially limiting access, increasing cost, or reducing competition. All right, this is another big thing. Like if you're on T-Mobile, they have partnerships with Apple TV, Hulu, Netflix. So if you're using their service, not only are you getting your membership to those sites paid, they're also guaranteeing that they're not going to slow down your internet if you reach your limits on those, right? So this idea of competition, fair markets kind of comes into play with net neutrality. And then lastly, how can internet censorship impact access to information and freedom of expression, right? So obviously internet censorship can restrict what information people can see or share online, which is probably going to limit education, communication, the ability to express opinions or access diverse, perspectives. Kind of all of that plays into it. So that's pretty much your Cornell notes for this week. So just, make sure you get those all filled out. Make sure you do your MCQ practice. Make sure you watch these other 3 videos. Again, they go into HTML, HTTP, HTTPS, DNS, TCP, UDP. Again, fault tolerance, redundancy, routes, paths. With some pretty good visuals that kind of let you see and kind of hear it from a different perspective other than just mine. I think it really helps kind of concrete that information for you. And then don't forget to do your weekly check-in.